start off with a fun little game here. Let's see if we can figure out which of these pictures was taken most recently. It's kind of hard, right? And of course, the answer to this is Miles Sabin. And Miles is really best known for his work on the Scala Eclipse IDE. But in his spare time, between this, he has worked on Shapeless. And the Shapeless project is really cool. And a lot of people, when they think of Shapeless, they probably think of things like HList and coproduct, which are sort of like these core sort of flagship parts of the library. But these are really just a demonstration, right? They're a demonstration of some techniques that we can use to do other really cool things, many of which are already in Shapeless. Shapeless is a series of tools for library authors. It's intended as a framework that allows library authors to create rich, typeful, generic interfaces that abstract over arity and present those interfaces to end users. But more importantly, Shapeless is kind of a playground for experimenting with techniques and idioms for type-level programming the type system. And these idioms basically give us a way, and these patterns give us a way of looking at code at the type level and actually being able to reason about it and write more of it and not kind of pull our hair out because it's a relatively clumsy system. Most importantly, though, Shapeless is not magical. There's no special secret sauce that's in Miles Sabin's copy of Scala C that is absent from my copy of Scala C. So we can do all of this stuff ourselves. And in fact, in this talk, that is exactly what we're going to do. We're going to create our own version of Shapeless. We're going to recreate a lot of these primitives that exist in Shapeless, and we're going to do it in this talk for fun and profit and your entertainment pleasure. So previously, some years ago, I gave a talk entitled High Wizardry in the Land of Scala. And in this talk, we implemented a very, very straightforward HList data structure. There really wasn't much to this. I didn't put much in it. There was basically just append, both at the value level and the type level. And that's basically where we stopped, because back in Scala 2.7, that's about as much as you could do. We're not in Scala 2.7 anymore. We can do a lot more. And in fact, this seems like a pretty good starting point for doing a lot more in this talk. So we're going to implement a whole bunch of functions on HList, similar to as they exist in Shapeless. And we'll learn about how to do programming at the type level while we're doing that. So here's the HList implementation from that talk. We have an HList trait that has an append function and append type. So type level function, value level function, and they mirror each other. And we just have two different cases that implement this. We have an hcons case and an hnil case. And they both implement append in basically the way you would expect. You notice we have to do this hnil not thing. I'll talk about that a little bit more in a second. But this is just basically getting around a bug in the Scala compiler. Whenever you're doing objects that you have to represent at the type level, you have to kind of do stuff like this. But you notice there's something a little bit weird going on here in the hcons case for append. And that's where we're sort of getting a type projection on this type t, which is a parameter that is of type HList. So it's sort of like open recursion at the type level. It's sort of this weird thing. It's kind of a neat trick, but this is how a lot of these sort of type constructor-based type level functions work. Now, what we're going to do to make HList a little bit more palatable to work with is we're going to implement some sort of syntactic stuff on top of this. So we're going to have a cons type that makes it easier to work with the hcons thing. We're also going to have a cons method so that when we have an HList, we can cons things onto it, just like with list. And you notice what we have to do is we can't actually put this method on HList itself because we need the specific type of the HList we're operating on. So what we're going to do is we're going to use this implicit syntax thing and enrich it onto HList. The only reason we're doing this is so that we can have the specific type of the HList we're dealing with. L extends HList. That's the specific type. So rather than just HList. It's a very common pattern when we're doing programming at the type level is, we go through all this effort to get a really specific type. We don't want subtyping to just throw that away and say, oh, actually secretly you just have an HList. We want the specific type to be carried along. So we're going to do a lot of this sort of thing in this talk. And by the way, the type hnil and val hnil thing, again, that's getting around a bug in Scala C, just so that we can actually call it hnil and have both the type and the value. But coming back to append, right? Append is a type level function. And it's a type level function that's implemented solely in terms of type aliasing. And it turns out that this is actually a very special sort of type level function. It is a context independent type level function. It's context independent. And as a consequence of being context independent, we get some nice properties. One of them is structural definition. So append is basically, there's really only one way to implement append over this HList, right? You have the cons case and the nil case, and everything just sort of falls out in this very sort of way that arises directly from the data. One of the things that's nice about this is when we're encoding sort of more complex programs at the type level, we get a really strong separation of concerns. We can define a way of sort of decomposing a structure using a context-independent type level function, and then we can use that mechanism for decomposition in other type level functions without having to redefine it. And we can talk more about this later. We won't actually see examples of where this is relevant because we're just working with HList, but for more complex data structures, this is a really serious concern. Context-independent functions, as the name implies, context-independent functions produce the same result, the same type, regardless of the scope in which you call them. So, users can't like import something or have some sort of weird definition that changes the result of this function. And more importantly, Scala C knows that users can't import anything or do some weird definition which changes the result of this type. It's always the same type regardless of where you use it. And so this allows Scala C to do some things and the language to do some things that we can take advantage of. This is also, because it's just a type alias, it's literally just a type, we can use it in any position that you can use a type in. This is something that you can't say about implicits, which are basically the primary mechanism that we're going to be using to program the type system. Implicits are tied to method definitions, which makes them a little bit constrained. But unfortunately, all of this is gone in Dotty. You can't. We sort of looked at Martin's keynote yesterday, but like this type projection thing on this sort of fixed type variable that sort of came from Magic Land and open recursion, you can't do that. You can't do that in Dotty anymore, and for good reason, right? There's a good reasons that stuff is gone. But for now, this is kind of an important technique to keep in mind. Unfortunately, this technique is also very, very limited. You can't really do anything other than basic open recursion at the type level. Like there's nothing more complicated than that. In fact, it's very, very straightforward induction. So anything more complicated than HList append probably cannot be encoded in this way. You can't do branching. So there's no like, if I see, some type over here, do this thing. If I see this other type, do this other more different thing. There's no type equivalence or anything like that. So the only thing that you can do is stuff that's very, very clearly structurally definitional. Things like, if it's an hcons, do this. If it's an hnil, do this other thing. You can do that. You can't do anything more complicated. And you can't pair these things with value level transformations. So of course, the append type function is paired with a value transformation, the append value level function. But we can only do that because it's trivial. Like this is a really straightforward function, and it's so straightforward that Scala C is able to sort of track the type equivalences through the proof and sort of keep things along the entire way. But Scala C is really, really aggressive about throwing away type proofs, and it loses the information that types are equivalent really, really easily. So most of the time, when we're doing more complicated things, we have to kind of hold its hand a little bit more and be explicit about when types are actually proven to be equivalent. So we really can't do that with context-independent functions. Type constructors are context-independent functions. And append is, like I said, it's a type constructor. But like I said, the primary mechanism that we're going to be using to program the compiler is not type constructors, but actually type classes. And type classes are context-dependent functions. Context-dependent. And there's some really, really important distinctions here. So context independence is good when you can do it. Like when it's an option to have a context-independent function, you should definitely do it, but it's really, really limited. So you get these nice properties like, it's usable in arbitrary scope and, users can't change it and whatnot, but, you just don't have that much flexibility, and it's a really awkward, unexpressive thing to work with. Basically, it's just lambda calculus at the type level. And, lambda calculus is Turing complete. I mean, you can do anything you want with it, but that doesn't mean it's particularly nice. So it's Turing complete, it's not Turing pleasant. So we're basically going to steer clear of this as much as we can. And instead of using context-independent functions, where we're sort of stuck doing a very, very limited set of things, we're going to use type classes and context-dependent functions. Context-dependent functions are really messy. They have a really awkward syntax. You kind of tear your hair out. This is really indirect encoding. But they're very, very, very powerful. You can do so many things with the implicit system, and nearly everything that we want to do is this. Basically, rather than giving us lambda calculus at the type level, which is what type constructors give us, context-dependent functions give us Prolog at the type level. Now, Prolog is still kind of a sideways language to work with, but it's clearly much, much, much more powerful and ultimately much more pleasant than lambda calculus, and this is in fact what we're going to take advantage of. So when we have context-dependent functions, we lose some flexibility. We basically, like I said, we're tied to function declarations. We need to be working with an implicit parameter block, which in Scala, like you can't just put that in an arbitrary type. You also have this problem that the structural decomposition, so the decomposition of your data and your sort of data types, is tied to the operation you're performing. So if you have some weird sort of complex structure and you want to define how to decompose that in one area over here and define that decomposition once, and then use that decomposition over in other sort of multiple type level functions without redefining it, if you're only working in terms of context-dependent functions, you're basically out of luck. Like, there's no way you can do that. You have to redefine the decomposition every time. Whereas if you can define the decomposition with a context-independent function, and then all of your operations with context-dependent functions, then you can actually have strong separation of concerns. So that's really powerful, but not always applicable. With context-dependent functions, what we gain is the ability to express arbitrary proofs at the type level. And we do this by expressing facts in terms of implicit values. And then Scala sees implicit search will go and assemble the proof for us and sort of put everything together and sort of generate the proof. One sort of random consequence of this is Towers of Hanoi, which is basically Prolog's version of like word count or Fibonacci, is actually really, really easy to express in Scala's type system. I'm sure all of us all day long need to write programs that only compile if they're a valid Towers of Hanoi solver, and now you know that it's possible. So in this talk, we've already talked about append. We're going to talk about 3 more functions at the type level, and they're all going to be of the context-dependent variety. We're going to talk about remove. Remove is a function that will just pull things out of an HList. We'll talk about map, which is the map that you would expect, and we're going to talk about nth, which Shapeless calls apply. I call it nth because I like syntax. So remove. What is remove? Well, remove is a type-indexed deletion function. You give it an HList, and you give it a type, in this case int, and it will remove all of the instances of that type from the HList and return the resulting HList to you. So in this case, the result is false cons HNil. And if I had a whole bunch of other ints in there, like 1 cons 2, cons false, cons 3, cons HNil, the result would still be false cons HNil, because it's removing all instances of that int. And clearly, this function is going to need to be context dependent, right? We're doing type equivalence here. We're giving an int type, and we're trying to look for all of the instances of that. And if it's not an int type, we want to not do something with it. There's a sort of a non-structural thing that's going on here, right? There's no material structural difference between a cons cell that contains an int and a cons cell that contains a Boolean. But we're trying to do something different with each one. So we need a context dependent function in order to do this. So how are we going to implement it, right? How are we actually going to make this work? Because this function is sort of going to be our canary in the type system's coal mine. Well, what we're going to do is we're going to put the remove function in the implicit syntax class that we defined earlier. Because again, we need the specific type of the HList that we're working on, just like we needed with cons. And what we'll do is we'll define a remover type class that will implement this function. The remove function itself on HList won't do anything other than delegate to this type class. And you should think of this not as a type class, but as an implicit proof. We're going to build a proof by sort of defining some facts, prove that we can remove a given type from the HList. And in the process of proving it, actually do the removal, right? So we've proved that it's possible to remove a type. And if it's possible to remove it, do the removal. Something that's interesting is if we were working solely in terms of phantom types, which is something that you do quite a bit at the compile time, we wouldn't actually even need to do the value level transformation. All we would need to do is just prove that the types line up, and that's enough for Scala C, and everything would just sort of unify out. So, but unfortunately, we do manipulate values because we're boring, and we are actually going to do that transformation. So here's what it looks like in code. We have this HList syntax class, remember, that the implicit class that enriches the HList type, and we have the specific type of the HList. We define remove, which takes some parameter A, and an implicit remover for type A and list L. So an implicit proof that given a list, we can remove this type from this list. And this type class has a particular return type. And this is, if you've never seen this syntax before, this might look a little bit weird. Because what we're doing is we're using a dependent method type, sort of a dependent output type from value R. So value R has some type out on it. We're pulling that type out, and that's the return result of our function. So there's a really common idiom in doing this sort of thing because of how various limitations in Scala's inference solver. So the type class itself is really, really, really trivial, the definition of it, right? We have, we take two parameters, A and L. We have this dependent output type that we talked about, out, which is a subtype of HList. And we have an apply method that we just apply to the HList and return the output type. But down in the companion object, we're doing something interesting. And this is one of those patterns and idioms that I was talking about, right? Shapeless does this a lot. Whenever you have dependent output types, you're accepting some limitations in the Scala compiler that I'll talk about more in a second. But it's very, very useful to sometimes bypass those limitations and move into a different context. Sometimes, instead of having a dependent output type, sometimes we actually wanted to pretend that out was just a parameter of remove. And remove would have 3 type parameters instead of 2. And so Shapeless gives us a pattern for doing this called aux. So the aux type is literally, it just takes A, L, and out, and it returns the particular type that is, remover of AL with type out. So this is a way that when you don't want to use dependent output types and you want to use type parameters instead, this is how you can do it. So why would we use dependent output types in the first place, right? This seems a lot of random trouble for something that I haven't actually explained yet. Well, it basically relates back to the way that Scala C kind of does things under the surface. Because Scala C is solving a solution, a constraint set, based on the implicits that it's able to find. And it's trying to solve a set of types such that it can find an unambiguous implicit for that set of types, and then it will sort of generate that for you. Now, in the context of remove, there's nothing really to solve, because we, as users, are specifying type A. But if this were a more complex thing, A would be a type that's part of the solution space, and Scala C is trying to pin this down. So A is basically a fact. You can think of it as a fact in the solution set. And if we had multiple type parameters here, multiple free variables, Scala C would be trying to solve them all. And they're basically solved from left to right within the parameter block. There's some exceptions to this, but more or less you can see it as drilling in and sort of reading from left to right. The problem is that some types cannot be solved in this way. You run into some weird problems. There's very famous bugs with SI2712, for example, is sort of a bug in this particular sort of quirk of Scala C. There's other problems that you can run into with de-aliasing and stuff like that, where Scala C just basically is going to refuse to come up with a solution, even though it's kind of patently obvious and unambiguous. So what you can do to get around this is use these dependent output types. Because dependent output types are restricted in many ways. They can't be used, they can't be part of a solution for a later parameter. And so because of these limitations, they force Scala C to ignore certain possibilities and sort of metaphorically compute the type rather than actually solving for it. And that will allow you to do some inference in cases where Scala C won't normally work. So just as a general pattern, if you have an output, sort of production that you're producing as a result of some type level computation, a sort of logical return type, if you will, you generally want to put it as a dependent output type. And if you need it as a parameter, you can always use the aux type. So there are, as I said, there are restrictions here. In Scala C, dependent output types can't be used in various things. Most notably, they can't be used in a computational continuation. So you can't have some type class that computes a dependent output type, and then another implicit proof that you resolve that uses that previously computed dependent output type to compute more things. That's not possible in Scala C. You can't derive new implicits as a function of out without using the aux type. And the aux type, again, that takes the dependent output type and moves it back into parametric position. You accept all of the limitations of parameters when you do that, but sometimes that's what you have to do. Multiple implicit blocks are the solution to this. There's a pull request out there that does this. Multiple implicit blocks solve so many things. So if you love Scala, you love implicit blocks. They're really, really, really great. And yeah. Yeah, Adrian is sort of scowling at me right now. The other thing that you can do, which will make Adrian scowl even more, is continuation passing style at the type level. Yeah, okay, now he's crying. But basically, if you're familiar with Scala Z's unapply or Katz's unapply, where it's basically this type class that takes another type class that it's going to implicitly resolve and sort of move along with the computation, this is another way that you can shift dependent output types back into sort of a continuation constraint space. We won't talk about this very much today other than this slide, because it's really a complicated thing to show. But if you need it, it is a technique that's out there. And until we get multiple implicit blocks, this is kind of the state of the art. So, yes, Adrian, that is a threat. So remover, how are we going to implement remover? Because we spent all this time digressing. How are we actually going to implement this type class? Well, we're going to start with a base case. And the base case is going to be the rightmost instance of the type that we're trying to remove, right? So the very, very final instance of it in the HList, we're going to try to remove that. And then we're going to have a rebuild case, which is co-inductive, and we're going to sort of be rebuilding the list and passing over types that we don't want to remove. So we just want to put them back in the output list. And then finally, we have a co-inductive remove case, which is, well, we already removed at least one type, so now we're trying to rebuild the list, but we ran into some more types that we want to remove. Because remember, this remove function doesn't just remove the first value that it sees, the first type that it sees, it removes all instances of this type. Now, if you look really closely at this, you'll see that there's an ambiguity here. Because the base case and the co-inductive remove case would, in theory, both apply in the same sorts of things, right? The base case is saying remove the rightmost thing, but we have to make sure that we've encoded in some way that it is truly the rightmost thing, not the any type, just the first type that it comes across. So fortunately, Scala's implicit prioritization system does give us a way of encoding this priority and disambiguating between the base case and the remove case. And the idiom usually shows up as this low priority implicits trait. Because it turns out that what Scala C will do is when it looks in companion objects for implicits, it's going to look first in the companion object itself. Then it's going to look at inherited members from the immediate supertype, then inherited members from that supertype, and so on and so on. But there's this strong ordering to it, right? It makes sure that all of the ones in the base type do not apply before it starts moving on to the supertype. So what we're going to do is we're going to put the more general, the less specific implicits in the supertype, in this case, the base case, right? So you notice that implicit def base, it doesn't take any implicit parameters, right? This will apply to any HList that has type A in it, and it will give us a remover for type A. So given an HList that the head of the HList is an int, and there's some more stuff beyond it, and we're trying to remove an int from the HList, we're just going to return the tail, right? That's what this implicit fact is stating. And you can see that in the remover.aux type. But clearly, this is completely unconstrained, right? It will just randomly grab any of them. So what we need to do then is also define the more specific co-inductive case in the base type remover. So the co-inductive case here looks really similar, right? We have some type A and we have an HList L, and the type A is at the head of the HList, but we furthermore have this constraint that we have a remover R, and we were able to remove type A from the tail. So this constraint obviously will not apply if we're not the absolute last type A that's in the list. So if we're the absolute last type A, we fall through to the base case. Otherwise, we're in the co-recursive case. And you can see right here, this is the sort of signature that you should zero in on if you're just sort of x-raying through all this boilerplate, is we're defining a remover of type A, or a remover for type A, given an HList that starts with type A. The co-inductive rebuild case is a little bit more complicated, but it's still the same idea, right? Now we're defining a remover for type A for an HList that starts with type B. And the result is, of course, just like we're taking B and appending it to the, prepending it to the HList that we're building back, right? The result type is the output of the aux. It's the third parameter, B cons r.out. And it turns out that this is actually all we need to do. So these three cases, these implicits here, these implicit facts that Scala C is going to solve for us, this is the remover type class. And remove now works exactly the way we wanted it to. Surprisingly, this is the most complicated implicit proof that we will see today. Everything else that we do from this point forward is easier. So good, congratulations. You've struggled through the hard stuff. Now we get to do the easy stuff, like map. Now, map on HList is kind of a funny function, because when I talk to people about Shapeless at sort of meetups and conferences and things like that, the very first thing that people say to me is, how does HList have map? Like, how is that even possible? And the confusion is obvious, right? If you look at the functor, which is this sort of defining signature for map, the signature for map takes an f of a and a function from a to b and returns an f of b. But what is a? Like, HList has many, many a's inside of it. Which one do we pick, right? How do we decide which one to pass to this function? Is it any? Like, what are we doing here? None of that actually makes any sense. So the confusion is really natural. So let's think about, if we were to define map, if we were to somehow do this on HList, what sort of primitive would we need to make it work? Well, clearly we would need a way of representing this function so that we can have a function that takes many different a's and maybe even returns many different b's. And we can select at compile time which case of the function we're working with. So a set of functions indexed by type. And we want to be able to choose the implementation of this function depending on which type in the HList that we're applying to. We want to do this at compile time. we're not going to be messing around with like runtime, right? Because if we were doing this at runtime, we'd just say every type is any and then do pattern matching and throw exceptions and all sorts of nasty stuff, right? We don't want to do that, right? We're gonna be solely at compile time because we're cool. And we clearly, if we try to apply this function to a type for which it does not have a case, it just shouldn't compile, right? We don't want to match error. It just shouldn't compile. So how are we going to do this? How is this actually possible within Scala? Is it possible? Well, it turns out the answer to this comes back to implicits, as everything always does. So implicit search considers the companions of types. Specifically, it's looking at the companion objects for all components of the type that it's searching for. So remover, for example. Remover in the previous example was a component. So the companion object was considered when it was looking for implicits. Now, classes have companion objects. We all know this. Objects are singleton instances of classes. So this raises a really, really obvious question. What is the companion object for an object's class? And the answer is the object itself. Who knew? That just like completely blew my mind. So this is really, in a very sort of strange way, right? Objects are like their own companion. Really, really weird. And it turns out that we can use this to do something extremely powerful. So what we're going to do is we're going to say, we're going to make the object self type, right, the class type of the object itself, a component of the type that we're trying to search for in the implicit search. And then the object that we're defining will have an implicit case, a case actually defined as implicit, for every type that we're trying to define a function for. And then when we apply the polymorphic function, we'll look up the case that we care about based on the inferred type. So given this inferred type, type A, we're going to find a case that sort of implicitly matches this. And it's really easy to give compiler errors if this is not applicable because it's just implicit not found. We can even customize this compiler error with an annotation. So it's really, really easy. It's also very easy to do polymorphism, like default cases or cases where other type classes are defined for a particular type. Because you just say, like, def default, square bracket A, close square bracket equals case, right? As long as it's implicit def default, then we're good. And really, really, really critically, this is going to have very good syntax and very good type inference. This is a point that I think we tend to overlook as library authors. We come up with this crazy cool idea for how to exploit some random bug in Scala to do something cool, and we're like, yeah, users are going to want to do this. But the truth of it is, if you're making users write some really crazy complicated syntax, so you sort of write down some really arcane type in order to use your trick, no one will use your trick. It's true. No one will do it because users care about syntax. So it's really important that whenever we're coming up with this stuff, we make sure that the type inference is happy with it because otherwise it doesn't matter and we're just sort of like shouting in the dark. So the syntax for this is really good and it looks like so. So here we're defining a polymorphic function square that's defined on 3 numeric types, int, float, and double. And it will literally square those numeric types and return the specific type that it's squared. So if we say square 4, it's going to return 16. That is an int. If we say square 3.14, it will return a double. There's no any valing here. There's no sort of coercing to double because that's horrible and you should never do it. It's all retained within the specific type, and all of this is done at compile time. And we can test this by trying to apply to a string, and lo and behold, this will fail. It just won't compile at all. So this is doing what we expect, and the syntax is not terrible, right? This is relatively pleasant syntax. So how do we define this? What does the machinery look like? Well, we're going to have a poly trait. And the poly trait is going to have an at function inside of it that takes a single type parameter A and returns a new type that in turn has an apply method in it. Now, if you've never seen this new curly brace sort of syntax, good. It's terrible. Don't use it. It's good for slides, nothing else. But basically all I'm trying to do here is make sure that users specify the A type and the B type, which is the output type of the function, is inferred, right? That's all I'm trying to do here. It's just, again, tricks for good syntax. So def apply B takes a function from A to B and returns a case, A, B. Now case is an inner trait, right? It's a type that's defined inside of the poly type, which means that the type of case is going to contain the type of poly, which is the thing that's really, really important to us. Case AB just has an apply that applies A and returns B. So that means that when we say implicit val is equals at int, the inferred type here is going to be case int int. Takes an int, returns an int. Could return something else. So this is the machinery. How does it actually apply? Well, the apply method on poly is relatively straightforward. It has two type parameters, A and B. It infers type A from the parameter that we're applying to, like int or double or something like that. And then it looks for an implicit value of type this dot case, A to B. And this is the component of the type that will have that Scala C is going to kind of go through and find the implicit values that we're looking for. Because this, in this case, is square dot type, right? Remember our example from earlier where we had square extends poly thing. Square dot type is the type that it's going to look in the companion for. The companion of square dot type is square, so it finds these implicit values, looks it up, and lo and behold, the square paren for application works the way we want it to. Pretty cool, right? We can even do fun things like emulate JavaScript semantics for integer addition, right? Because that's exactly the sort of thing that everybody wants. Yeah, that was a complete waste of time. But there are some downsides here, right? There's problems with this encoding. Problem number one, we can't parameterize the function. For example, like in the previous slide, we had add 1. It would be kind of cool to have add n, where you just take n is the thing that you're adding. Nope, can't do it. This is not as much of a limitation in practice as you would think. It's sort of surprising, but you almost never run into this. But it is a limitation, right? And it's something to keep in mind. There's no anonymous syntax. If you think about this as normal functions, right? We have def, and we have this named thing, but we don't have lambda. And that means that you have to name everything, and the syntax is kind of bulkier than you would like. That's kind of annoying. I don't know. It's hard to pass these things around as values, right? So this polymorphic function thing, it's difficult to sort of pass it around and be generic and abstract over it. Because what you need to do is capture the precise type, just like we have in our HList syntax class. You basically say, sort of square bracket p extends poly, right? It's not impossible, it's just weird. You just have to kind of like keep track of it. And that's sort of suboptimal, but it works. It works, and the syntax is sort of past the uncanny valley where people won't use it. As an exercise for those of you at home, you can implement a compose function for this, which takes two polys and returns a poly by function composition, and also a union, which takes two polys and returns a poly that has the union of all the cases within them. These are very easy functions to implement, and it's very instructive to do them. It teaches you a lot about how things work. So we've got poly. This is the primitive that we claimed would be enough for us to implement map. So let's implement map. We're going to put a map function on HList syntax that takes some p extends poly and an implicit mapper for some HList and for some poly p that returns an output type. Again, same pattern that we had before. We're just like completely empty function delegating to implicits. Mapper is just like we had before. It has an output type and an apply, nothing fancy. And it's going to have two cases this time. It's going to have the base case, which is for whatever poly that we're going on, where if you're mapping over the empty list, the result is the empty list. Nothing too crazy there. It really doesn't matter what poly we're given. However, if we're not in the empty list case, we need to actually do some more implicit work. So in the co-recursive case, we have a poly, a p, we have an HList L, and we're going to infer two types, A and B. A is constrained to be the type that's at the head of the HList, which you can see if looking at the mapper.aux thing. B is going to be the type that's at the head of the output HList, the third parameter in mapper.aux. And we're going to have two implicit constraints. One is that we can find a p hash case for AB. What that means is, given the polytype, look up an implicit case for type A producing type B. And B is the type that we're inferring here. So P in this case is the type component. This is the sort of square dot type thing, right? That will type infer. It will be the type of the class for the object, which means the object will be found as the companion for that class. And then everything will sort of work out. And lo and behold, if we do all of this, like that's all the machinery that we need, surprisingly, this example now works. So we have an HList, we have a simple transformation on that HList, we map the transform over the HList, and we get another HList as a result with the specific type. That's pretty cool. Like, that's really, really cool. This is all we needed to do it. Nothing magic, no crazy sort of compiler hacks or anything like that, just using the implicit scope. So this is kind of a general rule. When you're stuck, and you're trying to do something cool at the type level and you're stuck, try to see if you can abuse the implicit scope somehow. Because there's so many like corners and dust and like random skeletons hanging out. You can probably hide something behind that skeleton and it'll work. So this is a really cool thing to do. Nth. And as I said, Shapeless calls this apply. It's called apply when it's on list. We're calling it nth. It's literally just using an integer to index into an HList. And it looks like this. We have an HList, 42 cons false, cons nil. And we can get the 0th element, and it knows, the compiler knows that it's 42 of type nil, not of type any, of type nil. And if we get the 2nd element, 1, it's false. And if we try to ask for the 3rd element, this won't compile. So this is crazy. How do you do this, right? How is this even possible in Scala? Well, I mean, that's a good question. Well, assuming that it is possible, right? Presumably we need some way of representing numbers at the type level, right? Because we need to be able to represent these indexes so that we can find the specific type that we're looking at. So what if we have something like, I don't know, case object 1, case object 2, case object 3? This is a terrible plan. This is a terrible, terrible plan, and not just because it requires me typing for infinity. We should try to come up with something else. And what we can do is we can look back in the literature of logic and type theory and see if we can find a way of representing numbers, via some sort of recursive structure that would allow us to get at these things and manipulate them at the type level. And it turns out that there's already such a system. It's called Peano Arithmetic. And Peano Arithmetic is really straightforward. You have a base case 0, which is sort of empty, right? And then you have a successor case. And the successor case has inside of it another natural number. So what this means is that you can say that 1 is the successor of 0. 3 is the successor of the successor of the successor of 0. And it's really unpleasant to talk about, but it does work, right? This clearly encodes the entire space of natural numbers. We don't get negatives, we don't get decimals, but honestly we don't care, because all we're trying to do is index into an HList. Now, as you would expect, it's relatively easy to write a type level, sort of a function that converts a type level natural number, n subtype nat, to its integer value. And this is really, I do recommend you do this because this makes it debugging much, much easier. And the cases are straightforward, right? It's pretty trivial. The base case for 0 returns integer 0. The base case for the co-inductive case for successor returns 1 plus the inner type. And we can apply it to type suck int, or suck 0, and everything works sort of the way we would expect, right? Returns an int. This is the easy part, okay? So Peano Arithmetic gives us numbers at the type level, and they do have some sort of value level representation, right? Suck is a case class, 0 is a case object. So there is a value level implementation, but it's really awkward to work with. And remember what I said before about how important syntax is. It's really, really vitally important that our syntax is not completely eye-gougingly unpleasant to work with, because otherwise users don't care and our feature doesn't exist. So really what we want is what I showed on the first slide, which is that we're just using an int to sort of do this indexing, rather than using this suck sort of really sucky thing. So what we want is a function like this, right? That takes an integer, so nat from int, and returns a nat. Can we implement this function? Can we take an integer literal and lift it into a type level Peano natural number? Well, yeah, we could do this. We totally could do this. How? How, you may ask? Well, the answer is cheating. The macros are a mechanism for cheating in my abstract, and they're a mechanism for cheating in my talk. Macros are really dangerous. Don't use them. We're going to use them. They allow the introduction of new primitives. New primitives in the language, new primitives in the type system. They do not replace the existing type level facilities. I cannot stress how important this is. Let's say you have this crazy idea for like this cool thing you want to do in the type system in Scala, and you're like, I know how to do this. I'll just write a macro. No, don't do that. What you want to do is you want to compose new primitives that are constructed with macros using the existing implicit and type level mechanisms. Always try to do it with the existing mechanism. Don't just introduce primitives just because you can, because it's probably going to do it wrong, because I do it wrong and Miles does it wrong, and like it's terrible. Like it's awful. Like things will blow up and they're really, really brittle. So don't do this unless you absolutely have to and you've tried everything else. In this case, I tried everything else, it didn't work, so we're going to do a macro. So the fromInt function is going to take an int, return a nat, and it's going to be implemented by a macro defined in natMacros.materialize. Okay? This is kind of, we're starting to do the boilerplate that you do for macros in the current version of Scala. So what does natMacros look like? I'm glad you asked. It's kind of madness. This is a white box macro. It takes a context, imports c.universe, which is literally the entire freaking compiler. And then it has this materialize function that takes a tree and returns a tree. All of this is boilerplate. All we care about is the stuff that's in the middle here. Now the stuff that's in the middle here is going to match on the tree, and it's going to look for a constant integer literal that is greater than or equal to 0. And if it doesn't find one, it'll produce a compile error. But if it does find one, we just do this simple loop, which remember, this is running at compile time in the compiler. So we just do this simple loop to use quasi-quotes to construct suck, 0, and then we're done. This is generating a tree, which the compiler will use. And it turns out that this will, in fact, suit our needs. If we call nat.fromInt3, we get a value that is of type suck, square bracket, suck, 0. Pretty cool, right? Yes? Value types don't work? So the question was whether or not I could do 3.type. You can, sort of. The problem is twofold there. Number one, Scala C is really aggressive about throwing away value types. So, like, the compiler does actually have a notion of like 3.type. That is sort of in there. It does sort of work. But the compiler just very, very quickly tosses it out unless you do some other tricks. The other problem is that's not a structural representation. It's a nominal representation. So 3.type is completely distinct from 2.type. And there's no like relation that we have between them. So basically, in order to do the stuff we want to do, we would need a little bit more information than that. I wanted to do it that way, though. I wanted to, and I couldn't. So anyway, we have this nat from int thing. It returns the specific type. That's great. We sort of have this magical tool now for lifting integer literals to the compile level, but it's still not quite enough. Because remember our syntax here, given the HList, there's no nat from int going on here. We want users to just type x's.nth 0. Remember, syntax, syntax, syntax. We don't want users to type nat from int. We don't want them to have to explicitly convert from an integer to a nat. So it would be really great if there were some feature in the Scala language that allowed us to implicitly apply a conversion of some sort that maybe is a feature that we don't use very often because most of the time it blows up in our face. Well, nothing could possibly go wrong when we're doing this with macros, right? We apply the implicit modifier. We'll just throw that on the def. Nothing could go wrong. And it turns out in this case that nothing does go wrong, which really surprised the heck out of me. This works. I can't even believe it. This totally works. We're doing an implicit conversion as a macro. Wow. All right. So how do we use this? How do we write the nth function? Well, it's pretty straightforward. We throw it on the HList syntax type, just like we have in the past, and we're going to capture the implicit natural, the sort of precise type of the nat, n subtype nat, and we'll have some implicit type class nther, that for a nat and for an HList we'll find the nth value. This type class is very, very straightforward. It's just like map. It's so trivial we're not even going to implement it. But we have a problem here. And the problem is that we're trying to capture this precise type of nat by doing n subtype nat. And it turns out that Scala C will not oblige with this. Scala C will not trigger implicit conversions when you're doing this sort of like whole capture the precise type madness thing. And so our magical implicit conversion doesn't work. So we want our magical implicit conversion to work because we're cool. So how are we going to do this? Well, we have to be careful. What we're going to do is we're going to put a type n subtype nat on the nat trait itself. And then type n is going to be the specific type of the nat in question. So type n for 0 is just going to be 0. Type n for suck of n naught is going to be suck of n naught. Really, really straightforward. It's the specific type of the nat you have in your hand, which means now that down in the syntax, rather than saying n subtype nat, we're going to say n of type nat. And then in the implicit block, we can use dependent method types to shift that specific type n into the implicit parameter and use it in building the proof. And this is how you get around the problem. The n of type nat will trigger the implicit conversion, we'll get the specific type as a type member, and everything works. Sort of astoundingly, this now is functional. We've now implemented all of the machinery. You've literally seen it on a slide. I haven't left anything out here. This is all of the machinery necessary to make indexing into an HList work. Wow. Like think about what's going on in this expression, right? We have an implicit conversion from int to nat that triggers a macro. And the macro runs at compile time and generates a Peano numeral, which is represented as a series of nested type constructors. And then we use dependent method types to shift the specific type over into the implicit blocks and an implicit type class, which generates a proof that the indexing is valid for some Peano numeral and some HList, and then when we're done, we just generate a result because values are trivial. So like, that's a lot of stuff. And it's all hidden in that tiny little expression, and we did this. We should feel very proud of ourselves. So this is kind of magical, right? We're taking an integer literal, we're doing some things with it at the type level and the value level, where we're kind of lifting things around, we're getting them represented. So this sort of begs a really obvious question, right? With all of this stuff, does that mean that Scala is sort of like Agda or Idris, where it has like real dependent types that you can sort of, the value has a specific type that you can manipulate at the type level and vice versa? Well, I think the answer to that is yeah. Scala is a dependently typed language. The syntax is crazy, and it's going to break in random ways, but Scala is totally a dependently typed language. So all of the stuff that the cool kids are doing in Idris, you can go tell your friends that you can do it in Scala too. Adrian says don't tell them.
It depends on your definition of dependently.
So, okay, so Adrian is complaining that my definition of dependently typed is weird. We can have a smackdown later. But that's basically all that I have for my talk. We've talked about context-dependent and context-independent functions, and how sort of important it is to be context-independent if you can, but most of the time you're going to write implicits, right? You're going to be a context-dependent function. When you write a context-dependent function, you form an implicit proof, right? Think of this as a proof system, like Prolog or Coq or something like that. You form an implicit proof of your action, and you encode rules that the compiler will solve, rules that are implicit values. Then you use dependent output types to move the solved types into the output position without running into sort of de-aliasing bugs and weird stuff like that. Always abuse the implicit scope. Find the skeleton, hide the note behind it, do the jump scare. All of that's great. Scala C has lots of that stuff. Use it. And when in doubt, like when you've absolutely run out of options and not before, then you can use macros. Does anybody have any questions? Yes? What is Shapeless using for apply what?
Yeah, it's using a macro too.
Shapeless is using a couple of macros. For Shapeless's apply, yeah, they use the same macro that I have, basically. Except they didn't implement it with quasi-quotes because they did it before quasi-quotes existed. Shapeless also has a couple of other macros that are primitives, like the generic type class. That is there's a macro under the surface. But again, you compose primitives with implicits, so you're using the generic type class, sort of with other implicits in implicit search. Anyone else? In the back?
When you do the map over the
I think there's a microphone coming.
When you do the map over the HList, can you just construct the object right in the map call instead of defining it beforehand?
You mean the poly object or the HList object?
The poly object.
Yes. And in fact, so in previous iterations of this talk where I didn't forget what I was saying, I did actually talk about that. Because, yeah, if you notice the mapper type class doesn't pass along the poly value. We're just looking up the poly value via the implicit scope because it's a singleton. So yeah, that's exactly what you said it was. We don't have to bother passing things around at the value level because we have the type level. Anyone else? I think over there.
Are you guys dreaming up some ideas on how this will work when macros are no longer available?
Oh, God. All right, so what's being referenced here is the fact that macros in their current form are kind of terrible and being removed in Dotty. Especially, like, in Dotty, there's no parallel for white box macros. So critically, what I was using there was a white box macro, which allows me to manipulate trees and return a specific type rather than some sort of napped supertype. There's no functionality that allows us to do that in Dotty. Nothing. There's various ways that we can do some of it. So like polys still work, and other things still work as long as we have multiple implicit blocks. But this particular one is gone. So what I would like is for Dotty to have some mechanism for us to introduce new types at the type level, ideally without the full generality of white box macros. Because white box macros are terrible. Like, it's really, you can do awful things with the language by doing that. But right now, no such mechanism exists. I think we're probably out of time, so we should stop before people yell at us. Thank you very much.